When I turned 14, I received a very special gift: a telescope. That night, the moon wasn't around, so I pointed it to the brightest star in the sky, only to find out that it wasn't a star at all. It was Saturn. Seeing such a massive planet, so far away, appearing so small and insignificant, it's humbling. 15 years later, driven by the inspiration that this discovery kindled in my youth, I decided to embark on a journey in search for answers, in search of the history of the universe. My name is Diego Rasuris. I'm a musician and I live in Santiago de Chile. And 8 years ago, I began a journey. Back then, I was getting started in filmmaking, and I decided to inquire into the discoveries of my childhood. The sight of Saturn through the telescope, and how this discovery had a profound effect on me. I decided to explore the universe as an amateur. A couple of years later, a friend sent me this video.
Can you say hi to YouTube? Hey, how's it going? Here's an alien being spaghettified.
So this process accelerates the smaller the mass of the black hole. So as I lose mass, I start
In it, a world-renowned astronomer shared his knowledge with a class of students that looked as eager to learn as I was at the time. Encouraged by this new vision, I wrote him an email asking if he would be willing to grant me an interview. A few weeks later, and to my complete surprise, I received his reply. This was my first encounter with Alex Filipenko. I repeated this initiative with Neta Bacal and David Spergel from Princeton University, and Eric Linder, Saul Perlmutter, and George Smoot from Lawrence Berkeley Laboratory. They were all willing to meet with me and share their knowledge. What came later was a journey of exploration through their work and minds. During several years, this footage remained unpublished. Today, I want to share with you an experience of wonder, a knowledge that inspired their lives and mine forever. For thousands of years, humankind has looked at the sky in search for answers, trying to understand its place in the universe. In the pursuit of this goal, humanity has developed ever more complex thoughts to answer these great questions. For this documentary, I had the privilege of talking with these men and women that have given us an extraordinary knowledge with their studies of the sky. Through their work, these scientists have allowed us to understand better which is our place in the universe, our history and future.
I always think that the more we learn about the universe, in some sense, the more we realize that we're in one little spot in the universe, and that there's so much more out there besides us. So it gives you a real sense of perspective.
The Earth is but one tiny planet in an enormous galaxy that contains probably hundreds of millions of planets, perhaps some like the Earth. Our galaxy is but one among billions that we see in the visible universe. And the visible universe itself may be only a small part of what's out there. So we are tiny.
Princeton University is home to one of the world's most important astrophysics research centers. And in this privileged place, I interviewed one of the world's most influential cosmologists. Professor David Spergel has devoted his life to the study of the universe. His research has helped scientists get a better understanding of how the universe evolved since its childhood right after the Big Bang into the universe we see today.
We believe the universe started out very, very hot, very, very dense. In its first moments, it underwent a very rapid period of expansion. As it expanded, it cooled. About 300,000 years after the Big Bang, the temperature of the universe dropped to about 3,000 degrees above absolute zero. At that temperature, electrons and protons combined to make hydrogen. At that point, the universe became transparent, and this leftover heat from the Big Bang, this microwave background radiation, was able to travel freely from then to now. Mm-hmm. So we see when we look out what the universe looked like 13.7 billion years ago.
To put this in perspective, if the universe today had the same age as this 70-year-old woman, what we see in the cosmic microwave background corresponds to a picture of her only 17 hours after conception. This made me wonder, how is it possible to see the universe when it was only an embryo? How is it possible to look back in time?
Well, in astronomy, when you look out in space, you look back in time. The further out you look, the further back in time you go. We see the sun as it was 8 minutes ago. We see Jupiter as it was 30 minutes ago. We see the nearby stars as they were 4 years ago if they're 4 light years away, 10 years ago if they were 10 light years away. Distant galaxies, we might see them as they were 1 billion or perhaps even 5 billion years ago. When we look at the microwave background, we're looking back 13.7 billion years. We're looking back as far as we can to see the universe when it was only about 300,000 years old.
And this is how the universe looked in the beginning. All the stars, galaxies, and planets that we see today come from this soup of atoms and energy. Professor Spergel told me the story of how back in 1964, Bell Lab scientists Arno Penzias and Robert Wilson were experimenting with this antenna, and as they prepared it to scan the sky, they realized that it was receiving a very strange noise. After thoroughly checking their equipment, the noise remained. Without knowing, Penzias and Wilson had made one of the most important discoveries in the history of cosmology. They had detected the cosmic microwave background, a remnant energy from the Big Bang that gave birth to the universe we see today. This discovery was the equivalent of finding a picture of the universe when it was only an embryo, a picture of the universe that allows cosmologists to figure out its history. The next big step forward after the discovery by Penzias and Wilson was the work done by the scientists in the COBE team, who for the first time detected the fluctuations in the cosmic background radiation. The COBE team was led by Professor George Smoot, who in 2006 was awarded the Nobel Prize in Physics for his contribution to cosmology. Smoot and his team found evidence that proved that the universe began with the Big Bang, and that since then, it has evolved to take the shape that we see today. To achieve this, he used the COBE satellite to capture with greater precision the cosmic microwave background.
What you see is the universe is extremely uniform. But if I look with very great precision and detail to the part in 100,000, then I see these small variations. And what these small variations are variations in the amount of matter and energy there are in the early universe. They are then the seeds for galaxies, the clusters of galaxies and so forth.
The picture I have is seeing a baby at 3 days. And then we look and see what the child has grown into today as an adult. We compare the two, and we see many things have changed, but they still have the same DNA. And that's what we can do with the universe. We can look at the universe when it's 13.7 billion years old by looking at the microwave light. We can look in optical light at the positions of galaxies and also understand the universe today and compare it to the universe back then. And what has been a really remarkable advance in cosmology is the pieces fit together. And we have a coherent understanding of how these tiny fluctuations in the early universe grow to form the structures that we see today.
With this radiation, we get a picture of the embryo universe, like an ultrasound in a certain sense, that tells us what the future of the universe is. We can see how these perturbations are going to grow to be galaxies and clusters of galaxies. If the universe didn't have these very small variations, we wouldn't have galaxies. We probably wouldn't have stars, right? And therefore, we wouldn't have the Earth in the solar system, and so forth.
If the universe was perfectly uniform back then, it would still be perfectly uniform today. These are the seeds that grew to form galaxies, and of course it's the galaxies that contain stars and planets.
It's incredible to think that we owe our existence to these tiny differences of temperature in the early universe. And without knowing, we have all seen or heard them more than once.
While we haven't seen the microwave background radiation with our own eyes, almost all of us have heard the microwave background radiation, or at least seen it on our televisions. If you turn your radio between channels, you'll pick up static. Much of that static's coming from the Earth's surface, but a couple % of that static is leftover heat from the Big Bang. So you've all been listening to the heat from the Big Bang.
It's very difficult to imagine the cosmic microwave background, but from now on, each time you listen to this sound, you will remember that you're listening to the birth of the universe. The work of Spergel and Smoot has an immense value in this archaeology of the universe. Because as we unravel our origins through science, we're also looking for answers to the questions that affect us as human beings, in our time and in all times. And these scientists show us that we can understand most of the history of the universe, and that the history of the universe is also our history.
You can't be a cosmologist, at least I can't be a cosmologist, and study the universe on a large scale and a large time without having it change my perspective. So that when I look at the history of humans, it's a few thousand years compared to a universe which is billions of years, right? So it's more than 1 million times longer. So that universe is just, the history of humans in the universe is just a tiny, tiny speck of time.
Located 5,000 kilometers from Berkeley, the imposing Mauna Kea volcano, which is the tallest in the world, is home to the largest telescope on the planet. Professor Alex Filipenko has devoted his career to observing the most remote stars of time in these privileged skies of Hawaii. And he invited me to join him and his team during a night of exploration through the cosmos.
Most of my work is at optical wavelengths, so I look at things that can be seen with the eye, and I like it that way because I like to be able to see the things that I'm studying.
Inside the Keck Observatory, Filipenko and his team share their observation experience with other researchers from around the world. During that night, I could sit down with all of them and observe.
This is unbelievable. 4 locations before all this remote observing. We couldn't afford to bring so many people. But now, like, undergrads get to see how it's done and stuff. So it actually is really educationally useful, right? They're seeing tech work done being done in real time.
Okay. Well, then go ahead and put no. Position, please.
these scientists observe stars that die. And it's in this death that one of the most enigmatic links between man and the universe is unveiled. In the hundreds of years that man has been looking at the cosmos, only a few stars have been seen with the naked eye at the time of their death. All the other times, we've needed a mediator, a telescope.
Okay, yeah.
Okay, we got something.
We did?
Yeah. It's below. There it is. That's it.
Aha.
Okay, good.
Okay, good.
Okay, great.
Good.
Cool.
With the help of Keck Observatory, Filipenko and his team find a dying star.
Okay, we got something.
You think that right there?
Yeah, maybe,
Well, it's blue.
right,
Quite blue. It's quite blue.
right. Anything in the red? Oh, it hasn't read out
Hasn't
yet,
read out.
right. It's so slow. You know, we got it. Right, we got it.
I'm guessing the other
Yay.
two. I'm guessing the other two. We just.
Let me see the chart.
Yeah.
North is our object. Yep, yep, I agree. Good. And there, down at the bottom of the field, is that bright star. And there's those two faint doobies. It's a fantastic dip. There's a beautiful P Cygni profile in this on the red side spectrum of this object that we just did. It's huge.
NIN.
It's probably a type 1A supernova.
Oh no.
But whatever it is, it's deep. Yeah, it's probably a type 1A at a redshift of 0.1 or 2. 0.1. Yeah, excellent.
Right.
Good, okay.
The death of a star is followed by a gigantic burst of light. During some days, a single star shines as much as an entire galaxy. And in this transit to death, these bodies create new lives.
My group has been studying exploding stars, supernovae. They are stars that explode with tremendous violence at the end of their lives. And these explosions produce the very chemical elements of which we are made, like the iron in red blood cells, and the calcium in our bones, and the oxygen that we breathe, and the carbon in our cells. Those elements are produced in stars during their lives and during the explosions, and the explosions eject them into space, making them available as raw material for the production of new stars, planets, and ultimately life.
The stars that explode when they die are called supernovae, and during their life and during the explosion, they produce almost all the chemical elements of the periodic table, including those necessary for life, like oxygen, carbon, and iron. As the astronomer Carl Sagan said, "We are made of star stuff." And these stars that explain our origins are the same ones that allow cosmologists to figure out which will be the fate of the universe. From the first telescopes to sophisticated observatories, human beings have used their intelligence to get closer to the universe. We have found a knowledge that leaves us in awe with its immensity and its mysteries. But it has also made us capable of finding unsuspected links between us and the cosmos. These machines and this knowledge have unraveled the great questions we ask ourselves about our place in the universe. And the Keck Observatory is a pioneer in providing these answers.
Well, the most important discovery that we've made with this telescope, and also with Hubble and other telescopes together, has been the discovery of the accelerating expansion of the universe. So, collectively, using the biggest, best telescopes in the world, we found and studied distant supernovae. And from those data, we came to the conclusion that the expansion of the universe is accelerating.
In 1998, two teams of astronomers independently arrived at the same conclusion. The universe is expanding faster and faster with time. In other words, the space between galaxies is growing faster and faster. Filipenko was member of the team called High Z Supernova Search Team, which was led by Adam Rice and Brian Schmidt. The other team, called Supernova Cosmology Project, was led by Saul Perlmutter, who in 2011, 1 year after this interview, received the Nobel Prize in Physics for his discoveries.
We originally set out to find out how much the universe was slowing its expansion because we thought gravity would be slowing it down. What we found when we actually finally measured enough supernovae and put them on the graph, each one telling you an expansion at a different time in history, we found that it's not slowing at all. In recent years, it's actually been expanding faster and faster. And that was the surprise that the supernova told us just now about a decade ago.
How is it that through the observation of the death of these stars, these scientists arrived at a discovery that would change the course of knowledge and take the world of cosmology by surprise?
This is very similar to the effect that you always are using when you're watching cars approaching you on a distant road. If they're very, very faint and you know that that car is very far away, as it gets closer, you can tell how close it's getting by how bright the headlights are. So we are pretty good at gauging the distance to a car. Now, if it turned out that cars came in with much, much brighter headlights, you might be fooled occasionally into thinking one was closer than it really is. But generally, they're pretty standard, and so we know roughly the distance. The same thing happens with the supernova explosions, where there are some supernovae that are much brighter, some that are fainter, but there's a kind of supernova that are pretty much the standard ones that we work with. They're called type 1a, and every one of them is similar enough that we can judge how far away it is from its brightness.
That tells us how far back in time we're looking, because light takes time to travel from there to here. Encoded in that light from the distant galaxies in which the supernovae occur is information about the expansion of the universe, not as it is right now, but as it was long ago. So by looking at supernovae at many different distances, we're looking at different times into the past, and we can trace the expansion history of the universe. What we and Saul Perlmutter's group found is that the universe in the last few billion years has been expanding faster and faster with time, not more and more slowly as we had anticipated. So we live in an accelerating universe driven by some sort of a repulsive, mysterious, dark energy. It's fantastic.
Now we know that the universe is expanding faster and faster with time, driven by dark energy. But what does this imply for the fate of the cosmos? If the universe continues to expand with the acceleration suggested by the discoveries of Filipenko and Perlmutter, we face two scenarios. The first one is what cosmologists call the Big Freeze. In this scenario, the universe will cool as it expands and end in a cold and dark death. The second scenario suggests that stars, planets, and even atoms are torn by the expansion of space, produced by the so-called dark energy. This scenario is known as the Big Rip. Bad news for the universe. But what do we know about dark energy? What do we know of this energy that would be responsible for such bleak fates for the universe?
So this is one of the great puzzles that have really come into focus just in the last 10 years, but we now realize is some 75% of all the energy density in the universe. So we call it dark energy. The dark just means that it's a mystery, that we really don't know what it is. And energy, because Einstein taught us that energy is basically the same thing as matter, that they both have gravitational forces associated with them. The very, very odd thing about dark energy is that the sign of the force is the opposite. We think gravity is attractive. If we leave go of something, it drops to the ground. It's attracted to the Earth. Whereas dark energy almost acts in a repulsive manner. It pulls things apart rather than bringing them together. And this is directly seen in the expansion of the universe, that it's speeding up, as though you had this dark energy that's pulling it apart.
Cosmology has unveiled some of nature's deepest mysteries, taking a picture of the universe when it was only an embryo, figuring out how galaxies, stars, and planets formed, and that we're made of star stuff. Finally, and perhaps this is the question that will keep cosmologists busy during the upcoming decades, that the universe is expanding faster and faster with time, driven by a force we do not yet understand. But the unexplored terrain is vast. Neta Bacal of Princeton University believes that it is of paramount importance that we figure out these mysteries.
Years and years ago, we thought all that exists in the universe is just us and the stars and the galaxies. That's what we thought only going back to the 1930s. We thought that's all exists in the universe, and then it's fine and dandy and, we know everything. Now we came in not such a long time, we came with all these discoveries of dark matter and dark energy, that it just dominates. 95% of the universe is dark matter plus dark energy. So it's a very, very important, very fundamental for everybody, not just astronomers and physicists, but for the public, for everybody, for humankind to know, what is the universe made of? Do we have a lot of this mysterious dark matter or not? Do we have this mysterious dark energy, and what is it? Where did it come from? Why? We have to figure it out for the sake of humanity.
The work of Neta Bacal has been fundamental in trying to solve the mysteries of dark energy. This discovery could have unsuspected implications for the future of cosmology, but it also continues to shed light on which is the place that we have in the cosmos.
These are not philosophical questions. These are basic fundamental questions of what is the universe made of.
What is this all about?
What is it all about?
It's incredible to think that despite the enormous advances in our understanding of the universe, there are still so many mysteries. Will cosmologists be able to solve them someday? Or will the universe always hide some of its secrets?
This question is a personal question. It's a question I want to ask every single scientist. And it's about, how does all this we know now, and we didn't know for 500 years ago, so how does all this change us? How is a person different before knowing this and after knowing this? How does it change our view of the universe and our place in it?
There's in the Jewish tradition, an old story that says in one pocket you should carry a piece of paper that says, I am dust and I will return to dust. In the other pocket, you should carry a piece of paper that says, the universe was created for my sake. And we should be both humble, but also feel special. For me, the observations of the past 500 years give us both a tremendous sense of humility. The Earth is but one tiny planet in an enormous galaxy that contains probably hundreds of millions of planets, perhaps some like the Earth. Our galaxy is but one among billions that we see in the visible universe. And the visible universe itself may be only a small part of what's out there. So we are tiny. On the other hand, It is incredible what the human mind has done. When you go back and think back to the time of Copernicus and Newton, when we were just mapping the solar system and just trying to understand the very basic laws of physics. In the last 500 years, and this is really something done by, in the end, hundreds of thousands of people, at least millions when you consider all the people necessary to make these advances possible, have put together an understanding of the universe that, while far from complete, there are many, many things we don't know, have given us a much richer understanding of everything from how we've come from the first moments of the universe, to how life emerges, to how our minds work. And I think that should give us both a sense of humility and a sense of specialness.
Well, there are some days I think people are so silly, they're doing these crazy things, but the interesting thing is they're also capable of acts of great kindness and altruism and achieve great civilization kind of things that we can actually, in this basically one place in space and time, try and study the universe and understand the whole sweep of the history of the universe and the whole extent of the universe. It's actually an amazing intellectual achievement.
A friend of mine told me that, an older friend saying that when she was a child, her father used to take her out at night to look at the stars with the telescope. And years later, she asked him why he was doing that when he's not an astronomer and they weren't going to become astronomers. And he said it's because he wanted them to have a sense of perspective, that the little problems of our day-to-day lives aren't the big thing, that in some sense the world around us is much more vast, and that we should be thinking of ourselves as you know, part of a human population on a little planet, and that we're all trying to work together in a much bigger place than our own little petty problems at any given moment. And I think that's actually a very interesting, larger perspective on the world.
You can also look at it the other way, that we really are, in some sense, a very closely tied with the rest of the universe. So we mentioned these atoms that are formed, the elements that are formed in the early universe. So all of the elements that make up us, that make up everything we see, they came from the very hot early universe, plus the fusion that goes on in stars. So stars burn the elements down the periodic table, eventually the stars explode and spread those elements throughout the universe. So as humanity, we're very closely tied to everything else in the universe. We're made of stuff that occurred in stars, that occurred in the early universe. And so it's not only humbling, but it's also a source of pride, I think, that we have this connection and that we can understand the connection, that through the science we can actually learn about the universe and learn about ourselves in this way.
To me, astronomical studies have given a very moving, a very powerful image of our origins. We now understand how it is that small differences in the density of matter early in the universe due to quantum fluctuations eventually coalesced and grew into galaxies and clusters of galaxies. And within those galaxies, stars formed, again by gravitational attraction. And then through nuclear reactions in those stars, heavy chemical elements were made out of light elements. And then some of those stars exploded. And then new stars formed, and more heavy elements were produced through nuclear reactions. And then those stars exploded, and gradually there was this chemical enrichment that ultimately led to sun-like stars, rocky Earth-like planets, and ultimately life. To me, that is an incredibly beautiful story, a story of our origins. And we determined it through astronomical studies.
Years after discovering Saturn with my telescope, the Cassini spacecraft took this picture of Earth. This is how the Earth looks from Saturn. Here we are. And from here, and despite how small we are, we have been able of understanding some of the greatest mysteries of the universe, and along the way, get a better understanding of our own history.
Mm-hmm.